Our next speaker is Rüegg from Geneva, and he'll tell us about quantum magnets and switches for quantum spintronics.
Yeah, thank you very much. It's really a pleasure to be here. And yesterday I was a bit afraid that I would be the only guy not speaking about yttrium iron garnet. I mean, my whole life I haven't touched a single system with iron because the spin is too large, and that's certainly not in my quantum regime, let's say. So I will talk about quantum magnets, or the systems I have studied in this context. And when I put this title, of course, it meant that I had no clue what the answer would be. But during the course of preparing a bit this talk and also yesterday's presentations, I found it a very interesting new direction that people are now able to excite, magnetic excitations in insulators through the platinum contacts. I mean, 10 years ago we had similar ideas maybe, and there was no way to do it. And now I think there's many new experiments which are possible on quantum systems by having this kind of interfaces. So I work at the University of Geneva and at Paul Scherrer Institute. So the Paul Scherrer Institute is the Swiss national lab, if you wish. It's 40 kilometers outside Zurich, just at the German borders, so we are somewhere here in this direction. So the speciality really is that we have a zoo really of accelerators which we don't use directly to probe our samples, but we use them to produce secondary particles like neutrons or photons, and then we use these particles to study bulk materials. So you see here these different sources. So my own lab, we run all the instruments at the neutron source, the Swiss Palladian neutron source here. You see the Swiss photon source, SLS, that's a synchrotron. We also have muons here, which we use to probe local susceptibilities, also in bulk materials. There's also an ultra-cold neutron source, which is used for fundamental physics. And the newest addition now is on the other side. Here it's not visible anymore. It's actually Swiss free electron laser, where we produce very high intense pulses of coherent photons from the end of this year. So from a different perspective, you would see a 750 meters accelerator tunnel, where at the end you would have the end station to probe materials with this kind of resolution. So if you wish, so all these machines we use to study equilibrium properties and some dynamics, spin wave excitations, and this type of things I'm going to show you today. But very soon we'll also be able to see other dynamics, so pump-hope type setups, where we basically pump magnons and can see propagation through that. And these experiments we will do very soon now in the future. So what are we really interested in? So quantum magnets basically are model systems to study quantum many-body systems. And the link between different model materials or cold atoms and quantum magnets in bulk systems is essentially theory. So you could have something like a Bose-Hubbard type Hamiltonian, and then you can ask yourself, how do I see a multi-insulator transition? So you can go to ultra-cold gases and do this very classic experiment, find the localization of that ultra-cold gas particles in such an optical lattice. So there's many advantages in having this experimental system, but there's also many advantages working with bulk materials. And here on the right, you would have a summary of the bulk materials if you wish. And if you are in general interested in an analogy between these two different model systems, you could read our review article, which was done with Thierry and Oleg Chernyshov in Nature Physics a few years ago, where we actually show that some experiments can nicely be done in ultra-cold atoms, some with magnetic bulk systems. So the advantage here is essentially, if you, for example, use Newton spectroscopy, your coupling of your probe to your model system is very, very much understood in great detail. So here we know when we measure intensities of scattered neutrons, we know exactly the interaction of the neutron with the spins, and the information you extract is directly correlation functions. So we have seen very elegantly that you have to work much harder in Amir's case, where you have to understand these transitions, what they really mean. So you have to do a very systematics to understand what your experiments mean. The same is maybe true for cold atoms. You have to fold in, inhomogeneities of the densities, and this can all be done, it can all be understood, but it's also, in a sense, somehow a bit indirect. So sometimes you can also miss things because you have to convolute. Whereas I think here we have to work hard to get large samples. That's clearly a disadvantage, but then once it works, the information you can get out is extremely powerful. So that's why I think there's a lot to be done still in these systems, even if now there's a lot of work going on in cold atoms as well. So what is important for the society? So if you just go and do Google for quantum magnets, you find a very interesting company called Inner Soul Technologies. And then you can buy for $100, you can buy a magnet, and they recommend it that you put them on the engine block of your car. And then they say it makes basically atoms. It's a beautiful video, so it makes atoms to move in phase somehow, and then making your engine more energy efficient than it used to be before. You can be 100% sure that piece of metal or piece of thing you get is probably, maybe it's yttrium iron garnet, but it's definitely not a quantum magnet. So, you know, don't buy it. So, okay, for my work, I don't need a justification to be extremely useful in energy business, but it's a funny situation. So when I got the advertisement and the invitation, and thank you very much for this, to this workshop, even the picture here I found very fascinating. You know, it shows many things which you all want to achieve, let's say. It shows a device, you know, which says elementary excitation of some sort, which can be very colorful, and, you know, you see some kind of fancy magic going on. But I'm actually more the guy, I've never produced a thing like that. But what I typically do is try to understand the material here you see in between. And this is beautiful about this graphics, is actually that you see the atomic structure. At the end of the day, it matters a lot what material you use. And in a sense, you know, what we have heard about this in this workshop, it's, you know, using platinum, using yttrium iron garnet, it's relatively simple materials. Between what we do now in technology to what biology does in proteins or stuff like that, it's extremely trivial what we are doing now. So, you know, there's a lot of functionality which you simply don't understand. And the way to understand this better is actually to take here more complicated materials and try to understand them in a functional way. And there's a lot of things we can do there. So in a sense, you know, I really don't have an answer to how to produce these devices yet, but I can show you some materials which may have properties which might be very useful in this context. Nevertheless, there has been a contact between, let's say, the device world or or Hall effect measurements and what we usually do. And one example you could find in this recent paper of us. So this is lutetium vanadate. This is a pyrochlore structure, a structure we have not heard of in this workshop yet. There was very interesting experiments by Onose, so that's Tokura's group, where they measured basically a Magnon Hall effect in these materials. So you basically essentially make a temperature gradient, and then you see the magnons propagate. And because of a Charoshinsky-Moria term, they actually get an effective vector potential, you know, kind of making them go to one side rather than the other. And that is one example where essentially what you need is read information about the parameters in your system to try to understand all of these effects. There has been theories how this should happen, and the unknowns are essentially the exchange parameters, Charoshinsky-Moria vectors. Then you use a Newton spectrometer. Here you see two examples of spectra. That's actually a spin wave cone, you know, if you cut it at a certain energy. On the left you see the experiment. On the right you would see the simulation of this spectrum using two parameters, the exchange parameter and Charoshinsky-Moria. And that's the kind of information you can provide in this business. So at the end you would use this, plug it into your theory and try to understand the transport properties on a very quantitative level. I think the very good thing about magnetic model systems, and I add this to the list of possible systems, is to basically be able to do these calculations on a very quantitative way. So once you set these parameters, then exactly there's no way out. You know, you have to work very hard to get the things fit your other measurements. But going back to this picture, so I thought then what could I still talk about in terms of the switches? So some of the materials we study, they have been mentioned for example, like leathers. And I could now well imagine that because of these new possibilities with basically contacting platinum onto insulating materials, there's actually quite a few possibilities. And you can see this is very schematic. I've actually not thought this through in all detail because I simply don't understand all boundary conditions well. But in principle, what you can imagine is to have certain configurations. Let me start with number 3. Yesterday at the last talk, we have seen a very nice example where basically a simple XY magnet you can actually gate and then, you know, get supercurrent transport. And of course, there's many examples for XY magnets. You know, you can have full list of long tables of possible XY magnets. And they basically, the knowledge that they are XY magnets came out of bulk measurements or measurement of spin waves and things like that. So certainly the type of experiments which were proposed yesterday, they are essentially feasible, but you have to figure out what the right, you know, kind of scales are of the different anisotropy terms and so on. So the other two, you know, the yellow stuff and the orange stuff is now quantum dimer materials. So if you just say what a dimer is basically two quantum spins coupled in an antiferromagnetic way. I'll show you exactly what this means. And then you have a gap in the excitation spectrum. Now in an applied magnetic field, that turns into an effective XY model. And we have shown that then the transitions and high magnetic fields can be of the BEC type. So especially for such type of setups, then one could now imagine doing many different types of experiments, couple different condensates, maybe use the condensates on both sides to interface to an XY magnet, and so on. So there's loads one can do. We just have to figure out which materials are the right ones. And then this morning, I was extremely pleased to see that by the talk of Professor Saito. There's another possibility, and that's simply to take some of these one-dimensional materials, and we have seen beautiful examples for chains. There's many more. There's also ladder materials, so dimers, again in one-dimensional units, where basically you have an excitation gap, but with a magnetic field, you can actually control this gap. You can close it. You enter in an effective slot-in liquid regime. You can open a gap again at very high magnetic fields where you saturate. So this is exactly a super beautiful experiment we could just do as a next step now, starting from the ladders. So essentially you have these ladders running this way. You start with a gapped system. You will have a thermally activated behavior over the gap. And you can apply a field which can be quite modest. I show you later examples where a few Tesla does the job. You heat on one side and you can measure with platinum. But of course, we have not really played around with these interfaces and so on. It's much easier to use the materials we already understand. To interface now, have a platinum layer on top of a metal organic type material. This has just not been done so often. But I'm sure it can be done. It's just a question of the incentives to try. Okay, so let me now go to the real materials we study typically, and these are some examples. So these are structures now when you are very much interested in low dimensional behavior and low energy scales. So we'll find very beautiful examples in this metal organic business. So what's here on the screen, you see basically here on the right, you see single crystals of these samples. They are actually very large. This can be like a centimeter. So we want to have like a cubic centimeter of material, and we optimize the growth in this respect. And of course, it can also be done probably in thin films, which simply never tried. So the structure of the material here would be that you have the copper 2 plus is spin 1/2, so the quantum spin you want. And these structures basically form in one-dimensional rungs here, basically in pairs, and then the exchange is through super exchange through the halide side, which is here the blue one. So you see these one-dimensional structures, and then you basically get a layer of organic molecules sitting around these one-dimensional structures, and they like insulating, the individual units. So what would you expect from this? So simply from the structure, you could expect very one-dimensional behavior. And now in terms of exchange interactions, we have a good overview now. So exchange interactions, if you look at the examples this morning, so oxides, typically it goes from 1 to a few hundred millivolts. For the cuprates, it's several hundred millielectron volts. You can have halides, you go down. I show probably you have an example which is just above my boundaries, but roughly the ballpark is this. And organics can be a millivolt or lower. Then you have other types of exchange as well. So if you want to build up a quantum material, you certainly don't start with iron or yttrium iron garnet. That's 5/2, so you never touch this basically. So you start somewhere from copper, which is spin 1/2. You could have nickel, spin 1, then cobalt, and so on. So typically we stay up here and on this side of the bar if you want. But more recently, people got very interested in other systems like, J-effective 1/2 systems like the iridates. So a lot of people are now working in this regime with strong spin-orbit coupling, which could be very helpful in the business of transferring, some of the excitations from the platinum into the insulating system. In some cases, people go to systems like ytterbium 3+, which is also effective spin 1/2. And we have seen now examples for XY type systems, and there, of course, you would maybe stay down here with a rare earth, and then you get all of these guys. Holmium is usually a very high spin, easing spin. Erbium is a very good XY system, typically. So, if you look at the phase diagram, if you now want to go quantum with your devices, you basically, you just look around the materials which have been studied by many of us for quite a long time, and roughly, the design rules you can see here. Basically, it's very easy. Okay, so that's one example where this works very nicely, and we can produce very high quality single crystals. So now, how is the physics or the link to this effective many-body models I've mentioned before? So as a Hamiltonian, basically you start with something like based on spin exchange, like of this type. And as I said, the basic unit will mostly be a dimer, and the dimer has an energy energy scheme, which all of you know from undergraduate courses. So basically, you couple two spins with a dominant antiferromagnetic exchange. The ground state is a singlet, and the excitations are triplets, and there are 3 of these guys. Once you apply a magnetic field, you start to Zeeman split, and now the action really starts at the point where you start to, have the intersection of these 2 low energy levels. That's exactly where things start to be very interesting. So the ground state then acquires a finite population of these triplet states, and then you can start to engineer your states in a very interesting way. So if you go to an effective quasi-particle picture, that would be the one here above. So you have, of course, a hopping term that's based on exchange parameters, x, y direction. There's an interaction term, which is the Z component. And there is a chemical potential, which essentially is driven by the magnetic field. So if there's a gap, the chemical potential, you close it down. And in a very similar way, we have seen this, earlier in this session. So this is now kind of a powerful analogy. So I tell you that you have to find dimers, and then you have interesting materials which form one-dimensional structures, two-dimensional structures, and so on. And you can, at the end, you can map the spin problem onto a quasi-particle bosonic Hamiltonian, where essentially you have a hopping term, you have interaction term, and the chemical potential. And then if you have a real material, you can apply magnetic field, you can apply pressure, or play with the chemistry and have access to controlling these individual particles. So one of the phenomena we studied is BEC. So then you essentially come from a lattice of these dimers, and then you basically transform it to an effective particle picture. And then, if you have a site which is in a singlet state, that's the vacuum state in the lattice. Whereas if you have an excited triplet, then basically you have a particle here and that hops around. And we have shown that this in a magnetic field can lead to a BEC. I'll give you a bit overview pictures just in a moment. So once you apply a magnetic field first, there is a spin gap, there's no particle present. Once you close the spin gap, the chemical potential goes down to 0. Then basically you start to populate the lattice with these triplet states, and which can move around with hopping terms. And basically in this phase, you then get the condensation into a BEC 3D ordered phase at low temperatures. Again, the power here really is to control the densities of particles by having a critical field here where the density is 0, and having the saturation field where every site would be occupied by a triplet. Okay, so BECs are known from these guys, of course, cold atoms. Now we had very good examples for the. Let's show this one first. So from basically the Rüegg films, you have seen many presentations of this business. So this is examples of BEC in condensed matter systems. If you go back, there's actually another system in condensed matter where people have been looking at BECs, and that's exciton polaritons. That's a semiconductor in a cavity, and the work around this was done around the same time, actually 2006, and you get similar type of phenomena. A couple of years earlier, we have realized this analogy between the dimer states and BEC, and that actually was done in Japan first, where people looked at the condensation phenomena itself. So that's a phase transition in these 3D ordered phases. This was measured, critical exponents were extracted, and that was a first indication. Myself, we measured the excitation spectrum. This is just a trivial C1 splitting, but then in this condensed phase, you get at low energies, which is not shown here, actually the linear dispersion of the excitation we discussed yesterday, and these are the gap modes.
What's the order parameter? That's just physically.
The order parameter is that the spins basically on the dimer, because the field is on, you get an effective XY Hamiltonian. What you order then is basically the spin direction in this XY plane. Which
Kind of like candid antiferromagnet in a way.
it is like a candid antiferromagnet, has a uniform component, but the order parameter is the transverse momentum which
Like
orders.
Nail order within the plane?
Yes, that's right.
Okay.
The phase coherence is done by this long-range Nail order. Exactly. You can, there's this literature which is now nearly 10 years old or so, where this is all discussed in detail.
Do you know how large the anisotropy is within the?
Yeah, it's a very important question. So when these results were first done, we measured here the excitations and didn't find any gap. But what happens in reality is this U1 symmetry in the real material is typically broken by some kind of anisotropy in a bond. But in good materials, this anisotropy can first of all be extremely small, and second, it can also be modeled. You can calculate what then the gaps would be. So you can actually just add this as a.
Do you know what it is? in this material?
In this yeah, I know it's a 0.1% of the exchange parameter roughly.
10 to minus 4.
Yes.
Still to be significant. Like in some perovskites who looked at it's 10 to minus 5 of exchange parameter. It's still bad enough, you know, to try to overcome it as qualified. So
you know, you can apply the field in directions where essentially you get the smallest possible anisotropy. In this case, it's again 2 orders of magnitude smaller in this material. But in general, you have something which is, you know, you can find materials which are below 1% or let's say much below that. But of course, if you are now a very purist, you see, you can say that, you know, there is a gap in the excitation spectrum.
No, I'm worried about the threshold that have to overcome to start like driving dynamics.
Yes. So
even for small gaps, it's still could be.
So in terms of, you know, looking for currents, let's say, we thought essentially that, you know, because of these small anisotropies, this business is over. You see, you cannot find spontaneous. But then recently, you know, we thought, okay, maybe one could go to finite temperatures just above these anisotropies and keep these kind of pictures. But since then, no experiments were done. And I think with the new gating type technology, maybe there's a new way to do these experiments. Okay, so just to say BEC, you know, it's not only one example where in condensed matter you can find this. It's also the exon polaritons. It's also in this simple dimer system where the same picture applies. So, yeah. Okay, so now the tuning you can have, of course, we often say the cold atoms are very nicely tunable. That's certainly true, but actually these bulk systems also have quite some chemical flexibility. I have done quite some work under pressure where you can control the different exchange parameters as well. So there's actually very powerful ways to systematically control the Hamiltonians in such systems as well. And nobody has a problem to apply magnetic fields to, you know, 15 whatever Tesla these days, no problem. Okay, so what do we really find in materials now? So there are many examples now for such ladder systems. For example, if you are now interested in particularly 1D systems, you look now for materials where these dimers are aligned in one-dimensional structures. And then the picture would not be the one of BEC because you can't have it in 1D, but you would then go into the Luttinger liquid effective model, which we have heard of just before. There's many materials. There's some more for the list here. And I will show you now about these metal organic materials. Here, basically, which basically are very good realization of these Hamiltonians at a very low energy scale, which is very good for field tuning. So there's actually 2 versions. You can have a chloride and a bromide. Bromide usually has an exchange which is roughly a factor of 2 larger than this. And from this slide with a periodic table, you would expect something like a millivolt or a few millivolt of exchange parameters. And that's very good because even here, you know, you already have 2 different materials. So if you want to have something which has a bit lower gap, you just take the chloride. If you want a larger gap, you take the bromine. So there's some flexibility in that. Both have the same structure. So what is the excitation spectrum? This is old stuff. You know, you can excite this triplet and it propagates in a lattice along 1D and not along the others. But that's only half of the answer. So the 1 triplet excitations you see here, that's a sharp mode, exactly what I described. But there's also ways to excite 2 of these guys at the same time. You can do it in an incoherent way and get this kind of continuum which has a bow tie shape. If you excite 2 and they do, you know, a bound state and hop together, you gain some energy, and then you would expect a bound state to pop up here in the spectrum. So this is exactly what we can measure with neutrons. So neutrons have selection rule, it's delta S1, but you can choose all your Q values you want. So this is very powerful, so we want to measure exactly this in an experiment. The calculations you see here are DMR3 calculations done in the group of Thierry Chamarki and Corinna Collat at that time in Geneva. So we use modern spectrometers. They are big machines, unfortunately. So they have like big helium detectors, 50,000 pixels. Each of the pixels measures an energy spectrum at the same time. So this is at the Rutherford lab, for example, in the UK. You stick in your crystal, and then you can cover this kind of area in Q space. And basically what you do at the same time, you rotate the crystal. And when we do this, let's say for 5 days, we collect the full S of Q and omega information, the full dynamical correlation functions in 4D. So all Q information, all energy information you want. Okay, then you cut into several directions. You want to know what's dispersion in a ladder direction. Here on top you see that. On the left you see beautifully this magnon band. This is now the chloride material. The gap is 0.2 millivolt. The bandwidth is also 0.2. If you cut it in the other perpendicular directions, you would see no dispersion at all. So this is really beautiful 1D material. We fit in this with a theory, and you extract exchange parameters. Now everything we do from now on is basically based on exchange parameters which are fixed by this determination. So you can basically then calculate with DMRG the mode, including the intensities, the matrix elements, and you see very good agreement. Now the beautiful thing about the spin ladder is actually there's an extra symmetry. The ladder has a rung, and it's not only the momentum along the ladder which counts, but if you go transverse, you also have the transverse selection. And this gives you a very powerful way by symmetry to select if you excite a 1 magnon or a 2 magnon excitation. And this exactly we can do. We can cut through momentum space to see only the 1 magnon excitation. You see here, if we cut at a different transverse Q momentum, you will see only the 2 magnon sector. So we do exactly this, and you see here the data. So you have a little bit of leaking of the 1 magnon sector because of you have a finite width of the integration. But then on higher energies, you essentially see these 2 magnon bound states. The 2 magnon continuum is very broad, so this bound state is here, and you see very good agreement. So you can again see the excitations. You can use different theoretical models like series expansions. This is from Kai Schmidt's group, and you find similar types of structure factors. So this can be fully understood then basically both in experiment and in calculations. So now about high magnetic fields. So why is it so interesting now to play around and to first show you some data? So when you now apply a magnetic field, the magnetization curve would somehow look like this. You close the gap which we just measured, you get the finite magnetization, and this regime in the middle will be a Luttinger liquid. And we come back to this later. The excitations we measured as well, but I cannot discuss in all details. You see a spin-on spectrum at half magnetization. It looks exactly like a spin-1 half chain we have seen in your talk. If you go then to higher values, and I said that these systems could be like switches, you essentially go to fully saturated. If you apply a very strong field, all spins are field aligned. So you have ferromagnet, no fluctuations. That's your classical magnet you want. And the gap would increase from here 0 to a finite value linear with a gap. This you can also do in experiments. So then you would expect simply cosine type ferromagnetic spin waves with a quadratic dispersion here. And that's exactly what is measured. So we apply, in this case, fields in excess of 4 Tesla. And then you see these branches, which exactly are the ferromagnetic spin waves. So now in terms of, if you look for spin transport, and I don't know how to build the device, of course, but such a system is very beautiful. I mean, you essentially start here with a gap. You close the gap, you say a Luttinger liquid regime, and where you can tune basically the density of particles. You can go to the fully gapped saturated regime. And you can measure all of these different regimes in one sample in principle. That's quite cool. So how about thermal transport? That's the only thing we've tried so far, and this was seen before. This is this Von-Neumann compound, a beautiful presentation before with examples of chains, and this is a ladder. So you see the phonon peaks, and then this huge, basically, magnon transport. Now the special thing is, of course, this material has very large exchange parameters. So if you apply a magnetic field, essentially nothing happens. J is 100 millielectron volt. That's 1,000 Tesla. So if you apply a few Tesla, nothing happens. So here you would basically, this is one temperature, 105 Kelvin. So this is somewhere here. You apply a magnetic field, nothing happens. Okay, we thought, now we have a better system. We have one where we can go through all these different phases as a function of magnetic field. Let's try to do the experiment. So we did exactly this with this metal organic material. So first of all, you see that the anisotropy for the thermal conductivity is rather small for situations parallel and perpendicular to the ladder. That was very disappointing, and we never really understood why. So what we went on to do is to calculate what would we actually expect for the thermal conductivity in just an effective spin-on picture. So spin-ons are good in this system, low energy. You have these 2 lowest states, 1D, Luttinger liquid, everything fine. You can calculate, for example, specific heat as a function of temperature. That's the solid line. The points are the measurements. That's perfect agreement. So at low energies, your spin-ons do all your job. So you can calculate then what's the thermal conductivity you would expect for this system. We did the same calculation. You can see this solid line here, beautiful. And then we look at the measurement, and it does exactly the opposite, and with roughly a factor of 5 or so difference. So at that stage, we didn't know a good explanation for this. And here you see also temperature dependence. We were actually quite low in temperature. You see also some significant features. So for all the theorists in the audience, I think this would be a good challenge. Right now, I think our model was that we have relatively high quality samples, something like 0.5% of impurities. But for very 1D systems, maybe that's already enough to kill everything in a sense, that you come, after 100 lattice sites, you come to some site which is blocked. It's very 1D, so there's no way you can go with the spin on to the next chain and continue. So the idea was that you simply somehow stuck. And then, the field dependence of this process, we still have to figure out in a sense. My feeling is that that's, done by a super expert group, Thomas Lorenz, who did, and Sologobenko, who did some of the measurements presented before. So there's no doubt that this was done in a very good way. But on the other hand, there is maybe, problems how we contact this kind of metal organic samples. It's chlorides may react with some of the things we use. There's maybe more to be tried.
Question: How are the impurities treated in this theory?
There's no treatment of the impurities.
Why is the conductivity finite and bit conductive?
You mean the calculation is just a spin-on picture of just how what the spin-ons would contribute to the.
So it's diffusive even in the perfect.
Yeah.
In the perfect case?
So we had not we had not a model. We didn't have a model for the impurities or what we don't know what they are exactly. I mean, in principle, lead you put in.
Conductivity is not infinite without impurities.
No, not because we are at somewhat finite temperatures. The density you have for the spin-ons.
It's because of umklapp.
Yes. So yeah. So I not. So that's. So this is possible, of course, in any cases, but not.
That's the only thing.
Yeah.
Okay.
But now the way how this couples to the magnetic field, that's now the question, because in the spin-on picture you get incommensurabilities which are field dependent, and maybe there's a way so the umklapp scattering does this in a different way, but we didn't.
Experimentally, it's high. It's a blue curve that's experimental.
The blue curve, that's experimental points. So basically, well, this has not an offset or so. I mean, this is of course that's a pure measurements which has a phonon contribution as well. That's why it goes up. But in principle, you could there's a finite contribution here because of course it's not only from the spin-ons.
But this is lead material.
Yep.
Okay, so there are these critical fields below which at very low temperatures there are no magnetic excitations.
Yes, that's right.
But so in the middle range, about 10 Tesla or so, right, the discrepancy is much smaller so where you expect the finite population of your magnetic excitation.
Yeah, true, but it completely doesn't fit. You see, I mean, you would
I'm not
I mean, first of all, the critical fields are here. We know them exactly. You see, where the action should start here. That's somehow true. Where you have a big double peak structure here is another question. So I think the picture is just completely wrong here. So I cannot.
No, but so at low temperature, as a function of temperature, so the fact that there is a strong conductance in the limit where there are no spin excitations, tells that this conductance is done with some.
Yes, but this is the total conductance. You see, of course, in this case, you don't have a separation in energy scales between the spin-ons and the phonons. So you get that, if you measure at 400 millikelvin, you get the finite contribution still from the phonons. And well, it can be clearly dominant. In this case, let's say, in the other 1D materials, the energy scale is such that from terms of temperature scales, you see two peaks, and they are at different places. And that's very helpful. And you have the anisotropy, which helps. So you can subtract the phonon contribution, which is assumed to be isotropic. So you subtract, you have the spin-ons. In this case, the energy scale is 2 orders of magnitude lower. And so everything overlaps, and there's only weak anisotropy. So it's just, as I said, maybe it's not the end of the story in this business. But,
So are we sure that the lattices are not somehow weakly coupled in terms of picture?
They are very weakly coupled. We know, for example, in the Luttinger picture, I have a phase diagram a bit later, which I'm not going to be able to show, but in the Luttinger liquid picture starts at something like 1.5 Kelvin in temperature, but if you cool to 100 millikelvin, you see that actually 3D order appears. So there's very weak coupling between the chains.
Yeah, but you are very low temperatures there. It's 300 millikelvin.
Yeah, but it's only at 100 millikelvin the 3D coupling is strong. Yeah. But for your argument, basically, that you are above the 3D ordering temperature. So in this case, you are above the 3D ordering temperature by a factor of 3. So in terms of excitations, you are certainly in a regime, if this is true from, let's say, this paper from Bella Lake on potassium copper fluoride, you're actually in a regime here that the temperature is somehow populating mostly the spin-ons. There's nothing at low energies, which would be. Yes, so, you know, that's what the transport story. So we understand the magnons very well. I mean, there's no surprise in what the elementary excitations are. We even can measure the 2 magnon states very nicely. The transport somehow we tried, and that's the situation now. And I think with a new type of technology which is around for devices, we should just revisit these problems and try to measure something. And at the moment, I don't know exactly how to do it in detail, and I certainly don't know how to fabricate the interfaces and how to understand this. So there's a lot of work which needs to be done. I think it's very promising. So the last minute, I would then just show that you know, there's now a lot of chemical flexibility. So on your starting slide, you mentioned also many-body localization. That's a big topic right now, disorder in these problems. And for example, one direction we work on at the moment is now to try to start to take some of these ladder Hamiltonian, and then you can do many different things with them. There are many materials which produce frustrated systems and so on. We can have effectively doped systems. So one direction we are particularly interested in at the moment is to look at disorder effects. So one way to do that is you take now this material, and as I already showed, you have these 2 versions of it, and essentially you can now start to mix those. And that something interesting happens. You basically have the exchange path, which are the rung and the leg exchange parameters. So you do a mixing of chloride and bromide, and they statistically distribute on the lattice. And you can then basically make a statistical model for the variation of the J's in the ladder. So you can study effects of quenched disorder in this case, and look at the effects of localization and so on. So we have been doing that in the last few years now, you know, try to characterize all of these different compositions, extract exchange parameters from, so averaged exchange parameters, and also some from the excitation spectrum, and you find very beautiful effects. So here you see some examples of the data, now convoluted in this case also with resolution and so on. And on the right you see a calculation with exact diagonalization. And if you do this kind of disorder effects, what you find is that you get so indication of localized modes which appear below the excitation gap and so on. So we can now play also with these kind of chemical route, you know, to introduce disorder and see interesting effects there. Yes, so I think with this, maybe with this picture I could stop now. So this is actually the phase diagram, which for some reason I moved in front in the picture before I showed you the transport properties, but it disappeared. So these are quite nice structures, I would say, for low-dimensional systems. So the energy scale is such that, you know, it's a bit painful that you have to go to quite low temperatures to do the experiment, so room temperature is over. But on the other hand, you know, you clearly have a clear quantum system. You clearly have the ways to control your spin Hamiltonian biomagnetic field in a very continuous way. And we can actually do measurements now in terms of transport properties if we look for ways to produce these devices across a number of different regimes. And I think that would be very interesting. We can, you know, have the gapped regime, the quantum critical regime, the Lagrange liquid regime, and the classical ferromagnetic one in one sample if you want. So this would be very interesting. Just have to build a device to do that. So now, let me see.
Is the device, you mean, putting like plasma contacts?
Yeah, I think that's a bit maybe the yeah. So I'm kind of. We have now seen examples where this was possible to contact an insulator in this way, and how this would work here. And how to detect on the other side. One has to think about it. I don't know the answer to it yet, but some let me. just as the very last example, just to say there's other materials. Now I don't have time to show this. So this is basically other ladder materials with a bit higher energy scales, and there also you have bulky crystals, you know, which are actually closer to strontium copper oxide mentioned this morning. These are grown with image furnaces. You can polish this, and you can, this stuff you can actually just handle according maybe a glove box, but that's a glove box you buy. It costs $50,000, and you put it in your garden. So it's then you have to be very careful with machining, but this is possible. Certainly with this type of oxides, we can try many different things, polishing and stuff like that. For the metal organics I just showed, these chloride bromides, one maybe has to do some tests. but the crystal growth there is out of solution. So you could think of having a platinum substrate, and you just put it into a solution with this material, and you hope the stuff grows on top with an acceptable quality. Nobody has tried, so I think we can hope that this is possible. So then maybe I just simply finish with this. So I was now the quantum magnetism guy who has not much clue about the transport properties right now, but I think there's many different type of schemes, you know, we can really think about to do experiments. You have make proposals for XY magnets, and there's really many XY magnets which are known. I think this could just be done, and I think in terms of these dimer 1D systems, you know, there's all these experiments we thought were not possible to be done 10 years ago because we thought anisotropy would kill all the spin currents and so on. I think this is maybe not true if you now are able to, you know, basically force it in a different way and go to slightly higher temperatures which are above the anisotropy terms. And then I think we are back in business. There's many ways to engineer two different types of condensates. I've even shown you material where you have a chloride and a bromide you can just contact. And so yeah. I think, you know, I'm just, as I say, I'm not yet working in this business, and therefore I can dream of this, and I think there's a lot to be discovered here. Okay, thank you very much.